Welcome back, guys. It's Learning as a Hobby. In this video, I'm going to go through the exercise set for section 1.6 in John Taylor's Classical Mechanics. So let's jump right into the problems here and go over my solutions. Right. So the first question is this one. A golf ball is hit from ground level with speed v0 in a direction that is due east and at an angle theta above the horizontal. Neglecting air resistance, use Newton's second law to find the position as a function of time. Using coordinates with x measured east, y north, and z vertically up, find the time for the golf ball to return to the ground and how far it travels in that time. Right, so it's a ballistic motion problem, similar to the ballistic motion problems I'm sure you did in your, single variable calculus courses, and maybe even at the beginning of differential equations class. The only, I mean, here we're going to be using Newton's second law to set up the differential equation. Then we just solve them. So the initial position of this golf ball is at the origin 0, 0, 0 with the way that we're setting up our coordinates. So you have a golfer standing here at the origin, and he hits the golf ball with a velocity v0 due east. So the x-axis, we're considering the direction east. And the ball goes upward with it makes an angle theta with the horizontal axis. Okay, so the only force that's acting on the golf ball is gravity. So, at each point in the trajectory, gravity is pulling the golf ball down with a constant acceleration. So the acceleration here is negative g times z hat, right? It's in the z direction. The initial velocity that is v0, so we need to write down what the components are in the x and y directions. So the component of the velocity in the x direction is v0 cosine theta from the triangle there, just using trigonometry. And same thing for the z component, that's v0 sine theta, again by trigonometry. By the triangle here, v0 is the hypotenuse. This is, the x component, and this is the y component. So just using trig, you can figure that out. All right, and then we set up our equation, set up our differential equation with Newton's second law. All right, so Newton's second law tells us this: F equals ma. This is F here. This is ma. Okay. We notice here that we can actually, divide out by m just to get a simpler differential equation, which is this. Right, so the second time derivative of the position or the acceleration is equal to negative gz hat, which is what we already said here. And now we just solve the equations with the information that they gave us. Right, so integrate integrate with respect to time. That gives you the velocity. Right, so if you integrate this with respect to time, you get negative gt z hat plus an arbitrary constant v0. Well, not necessarily v0, but maybe I'll just call it c or something. Right, so c will end up being the velocity in the z direction, which the initial velocity in the z direction, which is this. So that gives you this part for the z component of the velocity. And notice that there's no acceleration in the x direction. So the initial velocity is v0 cosine theta, right? If you integrate 0, that shows that the velocity in the x direction is constant, and the constant that is the velocity in the x direction is the initial velocity, so v0 cosine theta. Right, and then integrate one more time to get the position. So r is equal to v0 cosine theta t times x hat, and integrating one more time here, you get v0 sine theta t minus 1/2 g t squared. The constants that you get from integration are both 0 because the initial position is 0. So that's the the function for the position of the golf ball at time t. So that's the answer to the first part of the question they were asking. I'll just circle that so we know that that's the answer to one of the parts of the question. And then the next thing they wanted us to say is, how long does it take for the ball to hit the ground again? And when it does hit the ground, how far has it traveled? So, the time it takes for the ball to hit the ground again, and how far did it travel when it hits the ground again. Okay, so we're going to find the time first. Let me go down. All right, the particle hits the ground when the z component, because that's the up and down direction, is 0. So you set the component of the function that we just found, the z component, set it equal to 0. So we get v0 sine theta t minus 1/2 gt squared equals 0. Solve that quadratic equation, which hopefully everyone knows how to do at this point, so I won't go through that. You get this as the solution. And then plug that in for t and for the x component, and that tells you how far the golf ball traveled after that time. So in other words, you take the x component of the position, plug in that t value in for that function, and that gives you this expression here, which I just simplified using a trig identity, which here, 2 sine theta cosine theta, if you remember from trigonometry, is equal to sine 2 theta. So I just rewrote it over that way just to make it look nicer. So you get v0 squared sine 2 theta over g. That's the distance, the horizontal distance that it travels. All right, that's the first question. Second question is also a ballistic motion problem. This is kind of a long one because there's a few parts to it. A plane which is flying horizontally at a constant speed v0 and at a height h above the sea must drop a bundle of supplies to a castaway on a small raft. There's 3 parts to this. Part A says write down Newton's second law for the bundle as it falls from the plane. Assuming you can neglect air resistance, solve your equations to give the bundle's position in flight as a function of time t. So let's start with that one first, and then we'll look at part B and part C after. Right, so again, drawing the picture and writing down the information that they gave us. This is all the initial value stuff that they gave us. So the initial position is hy hat. The initial velocity is v0x. So here we have our airplane, and it's traveling in the positive x direction at a constant velocity v0, and it's staying at a constant height of h, right? And then the acceleration is just due to gravity, because the plane is moving at constant velocity. So all along the trajectory of the bundle here, it's just being accelerated by gravity. So A is negative gy hat. Right, and then we can use that to set up our differential equation and solve it just like we did in part 1. Sorry, in the previous question, I mean. So you get m times r double dot equals negative mgy hat. Again, f equals ma. Notice here again, you can divide out by m, and that gives you this differential equation. And then just solve that the way that we did the previous one. So integrate with respect to time, and you get the velocity, which is this. You have to plug in the initial velocity to get the constants and everything, and then integrate that with respect to time one more time. That gives you the position, which gives you this. R is v0 t x hat plus, in parentheses, h minus 1/2 gt squared times y hat. And again, there you have to use the initial position to get the values of the constants. Once you do that, though, you get the position, which is this function here, right? So that's the answer for part A. Let's look at what they want us to do for part B. Right, part B says, how far before the raft measured horizontally must the pilot drop the bundle if it's to hit the raft? And then they're giving us some actual values for v0, h, and g. So they're saying the initial velocity of the airplane is 50 meters per second, which will be the same as the initial velocity of the bundle, right? The initial height is 100 meters, and g is 10 meters per second squared. Right, so let's do that. Solve that down here. Okay, so to figure out the time that it would hit the ground, we set the y coordinate equal to 0. So h minus 1/2 gt squared equals 0. Solve that for t. We get a plus and minus, but again, t is positive because we're starting our clock when we drop the package. So the time it takes for the package to hit the ground is square root th over g, which I probably should have plugged the values in for. I'll do that here. They said h was 100 and g was 10. And when you simplify that, you get was that 200 over 10, or square root 20, which is the same thing as 2 root 5 seconds. Right, so that's how long it takes for the bundle to hit the ground, 2.5 seconds. And then if we want to figure out, just going back up to the picture for a second, how what the horizontal distance would be. We know it takes 2.5 seconds for the bundle to fall to the ground. In that time, though, there's also a horizontal component. The package is taking a parabolic trajectory here, right? So how far did it travel horizontally? To do that, you just plug 2 root 5 in for the and the other numbers in for the x coordinate there. Where did I do that? Over here. So the x component of the position, you plug t1 in for that, which is the 2 root 5. You get v0 times square root 2h over g. Plugging in the numbers, you get 100. Whoops. And simplifying, you get 100 root 5 meters. Right. So that's how far it had to travel horizontally. Which means that the airplane has to drop the package 100 root 5 meters before the raft. This way, the package hits it exactly when it hits the ground. The raft, I mean, hits the raft when it hits the ground. Right. So that's the answer for part B. There's actually two answers here. This is one of the answers, and this is the other answer. There's a part C also. Right, within what interval of time, plus minus delta t, must the pilot drop the bundle if it is to land within plus minus 10 meters of the raft? So to do that, I use the x coordinate of the function that we found in part A. So I want to know what change. So I know it takes, let me get my highlighter. It takes time t1, which if you remember was 2 root 5. That's how long it takes for the package to hit the ground from 100 meters high. I want to know if I want to drop the plane, drop the package some small time before that, so that the package will hit the ocean or whatever it is, 10 meters either before the raft or 10 meters after the raft. So plus, in other words, this distance plus or minus 10 meters. Right. To do that, I just plug t1 plus or minus delta t into the x coordinate for the position, and I get an equation in delta t to solve. And when you do that, you get delta t is plus or minus 10 over v0, which I should have probably plugged the numbers in for. Plus or minus 10 over v0, I think was 50. So plus or minus 1/5 seconds, or in other words, plus or minus 0.2 seconds. Right. And then so the time it takes for the package to hit the ground is this. So the plane, if it wants to have the bundle hit the ocean 10 meters before the raft, it has to release it 4.5 minus 1, 4 times root 5 minus 1/5 seconds before, and then 1/5 of a second after, if it wants 10 meters after it. Right, so that's the solution to that's a solution to part C. Right, next problem is a inclined plane problem. A student kicks a frictionless puck with an initial speed v0 so that it slides straight up a plane that is inclined at an angle theta above the horizontal. I think there's there's a couple parts to this as well. So part A, write down Newton's second law for the puck and solve to give its position as a function of time. Let's do that first, and then we'll look at part B. Okay, so writing down all the initial information that they gave us. So here I have an inclined plane that makes an angle theta with the horizontal, and I get to define my axes here. So this is the origin where the puck starts, and I'm defining the direction along the plane to be the x direction, and the direction that's normal to that to be the y direction. Okay, and then just setting up our our picture here. The only acceleration that is happening is along the oh, why did I? This shouldn't be a y hat here. Sorry, let me erase this. Actually, I have to do it like this. Sorry, this should not be a y hat here. There should be a vector symbol on that. This distance, this vector here is in the y direction. Let me fix this. Should I do this in a different color? Let me do it in green just to distinguish it. This part here is in the y direction with the way that I define the coordinates. All right, so y is normal to the plane and x is parallel to the plane. Okay, so we're kicking the puck this way in the negative x direction, and we give it an initial velocity of negative v0, so going in the negative x direction. The acceleration due to gravity has two components. There's a component in the y direction, and there's a component in the x direction. Maybe I'll do those in different colors just so it's easier to see. The blue one is the acceleration due to gravity in the x direction, and the green one is the acceleration due to gravity in the y direction. So here, this is the initial velocity. This is the initial position, and then we can write down Newton's second law just using all the information that they gave us. So ma equals f. So this is f here. This is the acceleration due to gravity in the the component of it in the x direction, right? Because this cancels with that, right? The mass is not going through the plane; it's staying on the plane, right? So these two can cancel each other, and then we have the velocity going this way, and the puck is being accelerated in the opposite direction by this component of gravity here. All right, so we get all of our equations, and now we just solve the. Now we just have to solve the equations. So let's do that below. All right, so integrate with respect to time. We get this this value for the velocity. dRdt is g sine theta t minus v0, which is the initial velocity in the x direction, right? Then integrate again with respect to time, and you get r of t is 1/2 g sine theta t squared minus v0 t times x hat. The initial position in the x direction is 0, so again, that constant just goes to 0. All right, and then, so that's the answer. Actually, I should probably put a box around that. That's the answer for part A. And then let's see what they want us to do for part B. Part B says, how long will the puck take to return to its starting point? Right, so that'll happen when the x coordinate is 0. Right, so setting x of t equal to 0, you get 1/2 g sine theta t squared minus v0 t equals 0, solve for t, and you get the value, right? So this is the answer for part B. So like I said, relatively straightforward. 138 is another inclined plane problem. You lay a rectangular board on the horizontal floor and then tilt the board about one edge until it slopes at an angle theta with the horizontal. Choose your choose your origin at one of the two corners that touch the floor. The x-axis pointing along the bottom edge of the board, the y-axis pointing up the slope, and the z-axis normal to the board. You now kick a frictionless puck that is resting at 0 at the origin so that it slides across the board with initial velocity v0x, v0y, comma 0. Write down Newton's second law using the given coordinates and then find how long the puck takes to return to the floor level and how far it is from 0 or the origin when it does so. Right, so again, to start by drawing the picture, this is our inclined plane. It makes an angle theta here with the horizontal. This is my origin on this corner here. The positive x-axis lies along the bottom of the plane. The positive y-axis lies this way, and z is normal to the board. All right. So so we kick this puck going this way with an initial velocity v0, which is a vector here. Has components v0x. Actually, I can write it in vector notation. Let me do it that way. V0 x hat plus v0 y hat, and there is no acceleration in the z direction, so that component would be 0. Right, so our initial position is the origin. Our initial velocity is this, and then we can set up our differential equation from Newton's second law using the fact that the puck is accelerated this way by gravity. Right, there's a component of gravity which is so the gravity is pointing this way, right? Negative g. Sorry, negative mg is going this way. But we have a component in the z direction, and we have a normal force that's counterbalancing that, and we have a component of gravity in the y direction, and we have yeah, that's it, because it's not being accelerated in the x direction, right? So that gives us this equation here by Newton's second law. We can, again, notice we can divide out by m just to get a simpler differential equation. Solve that by integrating with respect to time twice and plug in your initial values. And when you do that, I won't go through the gory details because it's relatively straightforward. You get this function here. So r of t is v0 xt x hat plus v0 yt minus 1/2 g sine theta t squared y hat. Right, so that's the position function for the puck at time t. Right, and then, so what else did they want us to do here? Write down Newton's second law. Using the given coordinates, and then find how long the puck takes to return to floor level and how far it is from the origin. Okay, so similar type of problem to the one that we just did. So the puck returns to the floor when y of t is 0. So set that equation equal to 0, the y coordinate here, and solve for t. So you get t equals 0, or t is 2 v0y over g sine theta. And at that time, you just plug that in for x to see how far away from the origin it is. And it's plug that time 2v0 over g sine theta in for t and for the x coordinate, and you get 2v0 2v naught y v naught x over g sine theta. So that's the distance from the origin at that time, right? So very similar to the problem that we just did. 1.39. A ball is thrown with initial speed v0 up an inclined plane. The plane is inclined at an angle phi above the horizontal, and the ball's initial velocity is at an angle theta above the plane. Choose axes with x measured up the slope, y normal to the slope, and z across it. Write down Newton's second law using these axes and find the ball's position as a function of time. Show that the ball lands at a distance r equals 2v0 squared sine theta, cosine theta plus phi over g cosine squared phi from its launch point. And then they want us to show that for given v0 and phi, the maximum possible range up the inclined plane is r max equals v0 squared over g times 1 plus sine phi. Right. So start by drawing the picture, which I have here. Right. So we have an inclined plane that makes an angle phi with the horizontal, and we're defining our coordinates exactly the way that they said to define it in the problem. Um, we have our acceleration due to gravity in the the components of it in the x and y direction. So write down all the information that we have. The initial position is 0. This is our initial velocity, uh, and then using Newton's second law, we write down the acceleration, which is this. Okay, and then we solve this so we have to solve um, for the position of the puck or the ball or whatever it was at time t. And again, you just do that by integrating with respect to time twice and using your initial values to get to plug, find the value of the variables. Sorry, to find the value of the constants rather. And when you do that, you get this equation. Oops, this function here. All right, and then we can use that to solve what the other stuff that they asked us to find. First, they wanted us to, once we have that, they wanted us to show that the ball lands a distance here of this quantity from its launch point. So here, just to go back to the picture for a second, we're throwing this ball at an angle theta from the plane, um, or the hill or whatever it is that we're standing on, and the hill is at an angle of phi from the horizontal. So they want us to find, when we throw the ball, um, what is the distance that it's traveled up the hill, right? So um, show that the ball lands a distance of this quantity from its launch point. So in other words, they want us to show that this distance here, let me do it in a different color, that this distance here is that complicated expression that they have up there. So let's do that first. That happens when y is 0. So I can solve this problem by setting the y coordinate equal to 0. So in other words, this part here, set that equal to 0 and solve for t, right, which I'm doing down here. And you get that t has to be this value here, 2v0 sine theta over g cosine phi, and then plug that in for t in the x component for the for the position function. Okay, and when you do that, you get this expression here. Sorry, this whole thing rather. And when you simplify that using some trig identities, we get what they want us to show. So here, yeah, you have to use a few trig identities. For example, when you factor out the sine theta, you get this expression over here. And if you remember, that's equal to cosine of theta plus phi. That's just the sum formula for cosine. And then actually the next problem, we have to use another trig identity, which I'll show you when we get there. All right, so this is the answer. Oops. So that shows that the distance is what they said it was, right? Then they want us to show that for a given initial velocity and angle phi that the plane is, or hill or whatever is inclined at, the maximum possible range up the inclined plane is this maximum value here, v0 squared g1 plus sine phi. And I think I had to go on to another page to do that. Let me see if I can bring that up. Hopefully, let me just double check and make sure that the screen share works for that. Okay, so this is that problem continue, because Google Jamboards only let you write up to like 20 pages, and then you have to start a new one. So I just ran out of space there. All right, so this is that problem continue. So R is maximized when the derivative of R with respect to theta is 0, and where the second derivative is negative, meaning that you have a turning point and it's concave, the function's concave down at that point, right? That's when you get a maximum. If you remember back to your Calc 1 stuff. All right, so that's all I did. I just took the derivative of r with respect to theta. You get this expression here. And again, you have to use that identity, the sum identity for cosine. This simplifies to give you this. And that's equal to 0 when 2 theta plus phi is equal to pi over 2. I don't have to worry about coterminal angles because here, the hill can only be inclined from 0 to pi over 2, right? And I mean, you're not going to find a hill that's pi over 2, or at least not one that you're going to throw a ball up, and you know what I mean, right? So 2 theta plus phi is pi over 2, and solving for theta, then you get pi over 2 minus phi over 2, which you can simplify to pi minus 2 phi over 4. Okay, and moreover, if you take the second derivative of r with respect to theta, you get this expression here. And it's always negative because if you look at this expression, so here we have a negative sign. This stuff is all positive. And this is also always positive because 2 theta plus phi is between 0 and pi, and that's quadrant 1 and quadrant 2. And if you remember, sine is always positive in quadrant 1 and quadrant 2. So this expression is always negative because of that negative sign, which means that the um, the function that gives you r is at a maximum at that point. So plug in the value and you can figure out what the maximum, the value for t, and you can figure out what the, sorry, for theta rather, and you can figure out what the maximum value is. So here, when you plug it in and simplify, again, you have to use some trig identities. So for example, over here, I'm just breaking this up as the sum of two squares because cosine, if you remember, cosine squared phi is equal to 1 minus sine squared phi, and that's the difference of two squares, so you can factor it that way. And here, using the sum and difference formulas, you can see that this is equal to this simplifies to give you this expression here. Sorry, when you square it, you get this expression here. And then simplifying things, what do I get? What? Oh yeah. So here, sorry, this plus this is 1, and this is sine sine 2 phi over 2 again, but using trig identities. So sine of 2 phi over t is 2 is sine of phi, so you get 1 minus sine phi, and then notice that these actually cancel, and you get the quantity that they ask you to find. All right, so that's that problem. Kind of complicated trig stuff in there in that one, but other than that, not too bad. And also you have to remember your maximization, your optimization stuff from Calc 1. But all right, next problem. This is the last one for section 1.6. This was also kind of a complicated one, so we'll take our time and go through it one step at a time. 140, a cannon shoots a ball at an angle theta above the horizontal ground. Part A, neglecting air resistance, use Newton's second law to find the ball's position as a function of time. And then again, they're just telling us how to set up the axes. So use axes with x measured horizontally and y vertically. Part B says, let R of t denote the ball's distance from the cannon. What is the largest possible value of theta if R of t is to increase throughout the ball's flight? They give us a hint for doing that. Let's deal with part A first, and then we'll do part B. So part A, they want us to find the ball's position as a function of time. Right, so here, just drawing the picture, this is very similar to the other ballistic motion problems that we were just doing. It's nothing complicated. It's exactly the same procedure. So start by writing out everything you know, set up your Newton's second law to get your differential equation. You can divide out by m here again, and then just solve for the position function using the method that we've been using all along, right? And you get this. Okay, the hard part is part B. So let's now go to part B and see how to solve that. All right, so let me just read through it again. So R of t, let R of t denote the ball's distance from the cannon. What is the largest possible value of theta if R of t is to increase throughout the ball's flight? right? And he gives us a hint here. He says, using your solution to part A, you can write down r squared as x squared plus y squared, and then find the condition that r squared is always increasing. So that's what I did. So here, taking the sum of this, finding the square of the length of r of t, you just square the different components, so you get this. And when you simplify everything, you end up with this expression here. Okay, and then I want to, so the distance will be increasing with time if the square of the distance is increasing with time. So I want the first derivative with respect to time to be positive. So I'm starting by finding the derivative of this quantity here with respect to time. So here, if I differentiate, I get this expression here. Again, I want that to be positive because that'll show that the distance is increasing. Next page here. So solving for when this thing is equal to 0, because this is a cubic, if you look, this is a cubic polynomial equation. You can notice you can factor actually out a t from all of these. It factors this way, right? Either t equals 0, or solving this quadratic equation gives you this complicated expression here. All right, so we want this. Let me just going back up a second. We want this thing to always be positive. The derivative, right? We want that to always be positive because that means it'll be increasing for all t. Meaning that we only want the derivative to be 0 at the starting point, right? When t equals 0. So I don't ever want this to be, sorry, I don't ever want these to be real roots. I want them to, I want those to be complex roots. So, so that there is no other place where the derivative is 0, right? And I can figure out when that happens by, if you take the thing underneath actually what I did was I simplified first. Let me just, so going from here to here, I just factored out the perfect squares. You get this thing underneath the radical. When that thing is equal to 0, finding out when that thing is equal to 0 gives me sine theta is 2 root 2 over 3. All right. So this gives me the sort of the boundary point to where this expression is, how do I say it in words? It gives me the boundary to where that expression is starts to be positive. In other words, where you start to get real roots. So like if you graphed this function here, let's see, maybe I can do it on the next page. So it'll start, it'll look something like this, right? This is the value of theta that makes that expression, the 9 sine squared theta minus 8, starts to become positive there. So you start to get real roots there. But before that, you don't. So this would be from theta equals 0 to theta equals the arc sine of 2 root 2 over 3, which is approximately, I think it's like 70.5 degrees. Not exactly, but approximately. So as long as theta lies in this range here, you won't get real roots for this expression, this expression here. So that means that the only place where the derivative stops increasing, stops being positive, is when t is 0. Otherwise, it's positive the whole way. So the highest value of theta where that happens is this value here, right? So that's the solution to that second part. So for every angle theta between 0 and arc sine of 2 root 2 over 3, you have the derivative of this thing always being positive for all t greater than 0, which means that for all of those values, the distance from the canon is increasing with time, right? For the whole way. And that's the solution to all of the problems. So let me just stop the screen share for a second. All right, guys, that's the solutions for the problems in section 1.6. That's actually all of them. That was every problem that was in section 1.6. We only have to get through section 1.7, which is using Newton's second law, but doing things in polar coordinates instead of Cartesian coordinates, which is more complicated because the unit vectors are not constant with respect to time in polar coordinates. So the formulas are a lot more complicated in those situations. So we'll do that in the next video, and we'll end chapter 1 with the problems from section 1.7, and then we'll finally be up to chapter 2. And I want to go back then to the other books, but I just wanted to make sure I got past chapter 1, just because I want to start moving a little bit quicker. So I'll see you guys in the next video. Keep learning until that point. See you then.